Hi and Assalamualaikum. So today we will learn about chapter 13, which is the binomial and Poisson distribution. So for this chapter we have two parts, which are the binomial distribution itself and the Poisson distribution itself. So let's see the first part, which is the binomial distribution. So what is the binomial distribution? Okay, the binomial distribution is usually used to model situation where there are only two possible outcomes, such as success and failure. Okay, these are the following conditions that must be satisfied for the binomial distribution. First, there must be a fixed number of trials, and second one, the probability of success P must be the same for each trial, and the last one, the trials must be independent. So these are the examples where a binomial model or binomial distribution can be used. So let's see the first one, spinning a coin. So there will be two outcomes, which are heads and tails. So heads is the success and tails is the failure. So second example is throwing a die. So you will have either even number or odd number. So let's say you want to find the even number. So the even number itself will be the success event and the failure will be the odd number. Okay, the third one, playing a tennis match. So when you're playing such sport, it can be either winning or losing. So success event is winning and failure event is losing. And the last one is picking a card from a pack of cards with replacement. So S of spades, getting S of spades is the success event, and not getting an S of spades is the failure event. So that are the examples of binomial, where the binomial distribution can be used. Then we have examples where a binomial model or binomial distribution is inappropriate or not suitable. First one, playing a football match. So there are three possible outcomes. This is the reason why it is inappropriate. The first one, because when you are playing football match, it can be you can be winning the game or lose or draw. So there are three possible outcomes which not fulfill the three condition earlier. It should be only two outcomes so that it can be the binomial model or binomial distribution. Okay, let's see the second one, picking cards from a pack. Okay, this one is a pack. So the trials are not independent. Also, this is not this not fulfill the condition earlier. Okay, and then the third one, throwing a die until you get a 6. So throwing a die until you get a 6. There is not a fixed number of trials. Yeah, it can be the first draw you can get 6, or maybe the second draw you can get 6, or maybe the 10 draw, it's unknown. So this is not a fixed number of trial. So this is inappropriate to use binomial distribution. Okay, let's see example. A die is thrown 3 times and the random variable x denotes the number of 6 of 10. Okay, this can be modeled by a binomial distribution because first there is a fixed number of trials. Throwing the die 3 times, which is there are fixed n over here, which is your n equal to 3. And then the second one, each trial has two outcomes. Yes, getting a 6 is considered a success and getting any number than 6 is a failure. So you can have two outcomes. And then the third one, the trials are independent. Okay, what does it mean by independent? The result of each throw does not in any way affect the outcome of the other throws. This means when you have probability of x equal to 6 is equal to 1 over 6 for each row. Okay, this is the tree diagram. We can say from the tree diagram, probability of getting 6. 6. This is probability. This is other than 6. It can be 1, 2, 3, and 2, 1, 2, 3, 4, and 5. So the probability of getting 6 is 1 over 6, and the probability of getting the other numbers are 5 over 6. This is for the first row. And how about the second row? The second row also you will have from here, you will have 6, and this one also you will have other than 6. And for here, you will have also 6 and other than 6. So again, the procedure is repeated. The probability of getting 6, 1 over 6, and the probability of getting other number than 6 are 5 over 6. And then we continue until the third row, because we need third row, right? The n equal to 3, so 3 times throwing the die. So again, we repeat the same procedure. You have 6 and then you have other number than 6. So this is the probabilities for each rank or for each branch. You have the probabilities. Okay. So this is the value of x. Value of x here, your x is probably the event of getting 6. X is the event of getting 6. So in here you have 3. Why 3? Because you have 3 times of getting 6. 1, 2, and 3. You have all 3 6 over here. And how about this? How do we get 2 over here? Value of x equal to 2. Because start from here, you have 1. And then from here you get 1. Another 1. So we have 1 and 2. Up until here, this is not 6. This is other numbers. Can be 1, 2, 3, and 5. So there will be only 2 6 here and here. That's you get here 2. This is also similar. Why is it 2? Because from here 6, 1. This is not. This is cannot be counted, and then 2. So you have 2. How about this? Only 1 6 is obtained. Yes, because start from here 6 1. This one cannot be counted, and this one also cannot be counted. So only 1. Okay, and here you have 0 because all the value over here is not 6. It's other than 6. That's why this is 0. So the probability of each outcome. This is the column of probabilities. So you will have 1 over 6 times 1 over 6 times 1 over 6, which is equal to 1 over 6 to the power of 3, because you have 3 times here. And how about this? You only have 2 6 over here. We have the first one, the probability is 1 over 6, and then the second one will be 1 over 6, and then the third one will be 5 over 6. That's why it's look like this. 1 over 6 2 times, and then 5 over 6. Remember what we have learned before in the probability, chapter 10, probability. When you have tree diagram, you have to multiply along the branch. This is along the branch, right? So you have to multiply each of the probabilities. And so on and so forth for this one. So the probability distribution will be as follows. We have x, which is the probability of getting 6. There will be 0, 1, 2, and 3. Why is it up until 3? Because we only have 3 times of trial, n equal to 3. So the maximum you will have 6 is only 3 times. So these are the probabilities of getting x equal to 6. For 0, you will have 5 over 6 to the power of 3. And then for 1, this is what I have from the tree diagram previously. These are the one. Note that the distribution is discrete, as x can take only certain values, which are 0, 1, 2, and 3. We can also check it is a random variable, as the sum of all the probabilities is equal to 1. So if you total up all these probabilities of here, you will get it equal to 1. Okay. Then consider the outcome x equal to 2. How about when you have the getting 6 from the die throw just now, you have 2, 6. We can get the 2, 6 in the following ways. The first one, 6, 6, and then the third row you will get other than 6. Or you can have like the first row 6 and then second row other than 6 and then the third row equal to 6. Or you can have 6, the first one is other than 6 and the second one you have 6 and 6. So in for these examples you have 2 times of 6. Only 2 6 over here, 2 and 2. We notice each way of obtaining 2 6 has the same probability. Only the order changes in which the 2 6 occurred. So therefore, we could find probability x equal to 2 by finding the probability of 2 6 and 1 other than 6, then multiplying by the number of ways of choosing the 2 6 from 3. So in other words, it can be written in this: 3 choose 2. We have 3 times of trial, right? So out of 3, we only choose 2, or only 2 are success, which you only have 2 6 over here. So this is the way of writing it. Now we have probability x equal to 2 equal to 3 choose 2 times 1 over 6 to the power of 2 times 5 over 6. So why do you have to multiply these two? Because these are the probability of obtaining 2 6 and these are the probability of obtaining 1 6. Remember, these two you obtain from the tree diagram. You multiplied along the branch, so you get this. And don't forget to write this one. Example 2. A fair coin is tossed 3 times. Find the probability of getting no head, exactly 1 head, exactly 2 heads, and exactly 3 heads. So for the solution, let x represent the number of heads obtained. Then x follow the binomial distribution where your n equal to 3 and the probability of success equal to 0.5. So why is it 3? Because you have tossed the coin 3 times, so your n equal to 3. So we have this general formula, or this is actually equal to this, the previous one we have learned. In here it is written small letter of x, and previously we learned we use r, so it is actually the same. Small letter of x and r actually refer to the same thing. So the first one, you need to find the probability of getting exactly 1 head. So find the probability of getting no head. No head mean your r equal to 0. So all you need to do is just to substitute the value of n, p, and r into this formula given over here. So let's start with let's start with n. N equal to 3, r equal to 0, and then p equal to 0.5. We have p over here, 0.5 to the power of 0, which is your r, times q. Q, how do you get q? Q is actually equal to 1 minus p, which is 1 minus 0.5, so you get 0.5 over here, to the power of 3 minus r. 3 is your n and this is your r, so you get 0.125. And then you need to find the probability of getting getting exactly one hat. One hat means your R equal to 1 over here. So again, we use the same formula. The only thing that is different now is the R value. The rest is totally the same. Start with your N equal to 3, C R equal to 1, P 0.5 to the power of R, which is 1, times with Q remain the same, 0.5 to the power of N minus R. So N 3 and your R equal to 1. So you get this value. That is for x equal to 1 or 1 hat. Then how about exactly 2 hats? Exactly 2 hats mean probability x equal to 2. So all you need to do, again, you substitute the value of n, p, q, and r into this equation over here. So you get this value. And the last one is probability of getting exactly 3 hats. So over here, 3 hats mean you have 3, choose 3, 0.5 to the power of 3, q remain the same, n minus r. So your n equal to 3 and your r also equal to 3. Then you have this value, 0.125. Next is example 3. In a basket, 20% of eggs are damaged. If a random sample of 10 eggs is taken, find the probability that A, exactly 3 eggs are damaged. B, not more than 3 eggs are damaged. So we let X represent the number of damaged eggs. Then X follow the binomial distribution where n equal to 10 and p equal to 0.2. How do we get 0.2? Is here. The probability of the X damage is 20%, which is equal to 0.2. So this is the p value. So now we need to find A, probability exactly 3x are damaged, exactly 3x. So you have probability x equal to 3. Then again, we substitute into this formula NCRPR times Qn minus R. So you have your R now equal to 3. So your N is given here 10. You choose 3 times P is equal to 0.2 to the power of R times Q. How do you find Q? Q is equal to 1 minus P. So your P is 0.2. 1 minus 0.2, then you get 0.8 over here. Again, to the power of N minus R. N is 10 minus 3, you get 7. So you get this answer. And for B, probability of getting not more than 3x are damaged. Not more than 3 mean probability of x less than or equal to 3. So you have less than or equal to 3, you have probability x equal to 0, probability x equal to 1, probability x equal to 2, and probability x equal to 3. So we start with probability x equal to 0. Now your R equal to 0, you just substitute your R equal to 0 into this equation, and then you have probability x equal to 1. So now you have your R equal to 1. Again, you substitute this value into this equation. So you get this part, and then you have probability x equal to 2, or your R equal to 2 over here. So you substitute into the equation or the formula given over here. So you get this part, the whole thing over here. And probability x equal to 3 over here. So you just sum up all these values, then you get 0.8791. That is the probability of getting not more than 3x are damaged. Example 4. The probability that a random sample of a student love scenario program is 0.4. Find the probability that in a random sample of 8 students contains A, 5 students who love the program, B, less than 4 students who love the program, and C, at least 1 student love the program. So the solution, first we need to let X as represent the number of students who love the scenario program. Then X follow the binomial distribution where n equal to 8 and probability of success equal to 0.4. How do you get 0.4? Here, the probability of student love the program 0.4, and 8 is the number of student, 8 student over here. So we have this formula, or the general one over here. So now A, you need to find probability of 5 students who love the program. Probability of student who love the program equal to 5. So you have Px equal to 5. Then you have this NCRPRQ to the power of n minus r. So your n equal to 8, C 5 over here because your r is 5, times your p is 0.4 to the power of r 5, and then you have q. How do you get q? Q equal to 1 minus p. So 1 minus 0.4, you get 0.6. So this is your q. And then you have 8 minus 5, or n minus r. So you just key in this value into your calculator, you'll get this answer, 0.1239. That is for A, probability of 5 students who love the program. How about B, probability of less than 4 students who love it? Probability of less than 4 mean you have probability x equal to 0, x equal to 1, x equal to 2, and x equal to 3. So you total up all the probabilities for this value, x1, x0, 1, 2, 3, and x0 until 3. So you get this answer. Again, still you use the same formula, NCR P to the power of R, Q to the power of n minus R. The only things change is the R value over here. See, this one is 0, this one is 1, this one is 2, this one is 3. Okay, the last one, probability of getting x greater than or equal to 1. Probability of at least one student love the program. So we have this. Or we can write it down as 1 minus probability of x less than 1. So 1 minus probability x less than 1 means probability x equal to 0. So you have probability x, you just substitute, you find the value for probability of x equal to 0. You substitute the value of r into the formula over here. So you get the answer. So this is the answer for at least one student who love the program is 0.9832. Then we have the binomial probability tables. Usually we use the probability, the less than formula, or the less than table. There are two tables actually. If you can Google it. The first one will be the greater than, for the greater than table. The second one is the less than table. What I mean by less than table is over here. The formula is given here, but the sign over here is less than. So you know it. This is the less than table, or the less than formula. Okay, not over here. Probability of x less than or equal to r is probability of x is less than and equal to r. This is the one. So I'm going to show you the table, the binomial probability table, the less than table. But at first we need to see the example. X is a random variable such that x follow binomial distribution with n equal to 5 and p equal to 0.3. By using the binomial table, find A, probability of x greater than or equal to 3, then probability x greater than 3, and so on. So how do we solve this? We're going to use the binomial table with the less than sign. So let's see. Sorry, I have to show you side by side. And then we open another one. This is the table. So we have previously we are given x follow the binomial with n equal to 5 and p equal to 0.3. So we're going to see this is the cumulative binomial probability table with the less than sign. Here you can see the less than sign. Okay, now we have n equal to 5. So you're going to refer to this column. N equal to 5 is over here. N equal to 5 over here. And then P equal to 0.3. So P is here. You're going to see or to refer to 0.3. Alright, this is 0.3. So you're going to refer to this column, 0.3. And we have the first one, R is 3. Or sorry, we need to break this one. Probability of x greater than or equal to 3, or we can write it down in this form. Since we have this one is greater than sign, so we don't have greater than table. Now we are using less than table. See the less than table over here. So all you need to do is you're going to change the sign over here. How you going to change the sign is by rewrite the equation. So you have probability x greater than or equal to 3 actually equal to 1 minus probability x less than or equal to 2. So this is actually the same with this. Greater than or equal to 3 equal to 1 minus probability x less than or equal to 2. So you have now 2 over here. So you have 1. So you write it down 1. The thing you need to find is this part. Probability of x less than or equal to 2. So R, you already have your N and P. Your R now is 2. So back to the table. We're going to refer back to the table. Previously, you have N equal to 5, this part, and your P equal to 0.3, this column. But now you already have your R equal to 2. So R equal to 2. So you're going to refer to this thing. See? 0.837. So that is the answer for that. Probability of x less than or equal to 2 is equal to 0.837 here. 837. So you're going to minus that from 1. You get 0.163. So that is the answer for the first one. Okay, let's see the B. Probability x greater than 3, which means 1 minus probability x less than or equal to 3. We need to rewrite it because the sign over here is greater than. We don't have greater table, we only have less than table. See over here less than. So we rewrite it, we rewrite it into this 1 minus probability x less than or equal to 3, which is equal to 1 minus, okay, back to the table, you still have 0.3 as the P and 5 as the N, but now your R equal to 3. So your R equal to 3 is this one. See? Your R. This is for R. R or C over here. R. So you have 0.969. So you write it down, 0.969. 1 minus this value, you get the answer for that. Okay, let's see C. Probability x less than or equal to 3. So since this one is less than or equal to 3, which is similar to the table, you don't need to rewrite the probability. We can straightforward check to the table. So the n equal to 5, r equal to 3, and your p still 0.3. So this is it, 0.969. So you get the answer straight away. And D, probability of x less than 3. Less than 3. So we can write it down as probability of x less than or equal to 2. Since this is the table of less than or equal, so this can be written as this. So x less than or equal to 2 is actually this. See? N equal to 5, your R equal to 2, R equal to 2, and your P over here, P 0.3, this one, 0.837. So you get the answer. And for E, probability of x equal to 3. Probability of x equal to 3 is actually equal to probability x less than or equal to 3 minus probability x less than 3. So the two things over here, you already found it previously. So we just substitute the value. For this one is this, 0.969. And for this one, we get it in here, this. So this is the answer.